One of the core topics in mathematics is linear algebra, and for good reason. We're usually taught linear algebra using the real numbers, or complex if you're special, but today I would like to take a different angle of attack and reinterpret some of these topics in a different context. To do that, I'll utilize a game you may or may not know about. Lights Out is a game about, as the name suggests, turning off all the lights on a board. Each light also serves as a button that toggles its own state as well as the state of any neighbors it has. The main difficulty comes with this last rule since, say, turning off this light turns that one on, and now we're messing everything up. Fortunately, there are only two states, off or on, so there isn't too much to worry about. That being said, one could introduce a game with more light states, but you can definitely get away with ignoring anybody who suggests such a psychotic thing. Wait. The other saving grace is that the order of button presses does not matter, since each button has a fixed collection of neighbors it toggles when pressed. The when for these toggles is irrelevant. The only thing we care about is how many times they get toggled. This fact allows us to represent this problem in the language of linear algebra. In this video, I will discuss how we can utilize finite fields, in particular the binary field, for this problem, and discuss one of the main algorithms used for solving linear equations. At least in this context. Since these lights have only two states, it's reasonable to look to modular arithmetic. I'll somewhat quickly go over it here, but there are far better resources that cover the topic in more depth. Each of these buttons toggles the state of the light in the center. That is, the total number of button presses made among all the buttons is how many times that central light toggles. For now, we'll only look at this central light, so we only need the total number of button presses. If the light has a number attached to its state, we can add the number of button presses and set the light on or off, depending on whether that number is even or odd. Viewing it this way, we can see that the only thing that really matters is evenness and oddness of these numbers. One way of looking at it is to treat the state not as a single number, but as the collection of all even numbers or all odd numbers. Since the words even and odd are a bit unwieldy, at least compared to single-digit numbers, hey, we're doing math here, not elementary grade writing. We're going to instead write 0 and 1. The effect is still the same, it's just that now we're adding with all of, or perhaps some arbitrary choice from, the even numbers and odd numbers. This 2n here encapsulates all arbitrary choices, since choosing any integer for n can give us any other number within that same category. When adding two numbers, I'll use a subscript to differentiate these values so that they stay arbitrary, even relative to each other. In the literature, instead of this symbol n, sometimes a blackboard z is used, the symbol for the set of all integers. This is in reference to the more esoteric concepts of normal groups or ideals and quotient groups or rings, but that's way out of the scope for this video, so I'll just stick to this. The nice thing about writing things this way is that if we wanted to repeat the same action of button presses, we're just adding the same number multiple times, which sounds kind of like multiplication. In fact, it is just multiplication, and the result, surprisingly, or probably not, has the same even-odd predictability. We can check this using the same add 2n strategy. Speaking of which, this same sort of logic extends to working with larger numbers of states by replacing 2 with that number. We could go much further in depth into modular arithmetic, but that's not the main point of this video. Before we move on, though, I do want to make a quick remark for higher bases. For any base, only this number, what's pretty much just a remainder, matters. So you can use, say, the values 0, 1, 2 for a tri-state button, and the addition of multiplication tables will look like this. For more control on our button state, we may also want to take a look at subtraction and division. You know, the other two basic operations of a number system. These amount to finding additive and multiplicative inverses. If you're familiar with how to solve linear systems, you'll recognize their importance, so please bear with me. These are rather trivial for base 2, so I'll look at them for a general base b. Say we pressed some buttons and we want to undo our action. For base 2, we can just hit the same buttons again. In general, we can repeat the same action b minus 1 times, and that'll get us back to 0. The multiplicative inverse is relevant if we want to figure out how many times to repeat an action in order to have its net effect be just addition by 1. Once again, this is very straightforward for base 2. If the action's 0, well, we can't. This is pretty much equivalent to the whole division by 0 thing. If it's 1, well, we're already done, right? I'll say, though, that this only makes sense for bases of prime numbers. Inverses don't exist for factors of b, and we can see this by distribution. On screen is a short proof of this result, so feel free to pause. I won't be going anywhere. The fact that inverses exist, for non-zero values of course, in prime bases is a result of Fermat's little theorem, but I'll be leaving out the details. These two inverses will come in useful later. Or perhaps not if you want to stick to base 2, that's completely understandable. What we've been discussing here may be referred to the finite fields of prime order. The important thing to note, though, is that we have the 4 basic operations, just like the real numbers we know and love, and we will be putting all 4 operations to use when looking at arrays of lights and buttons. You know, the whole point of this thing. As we mentioned before, the order of button presses doesn't matter. This allows us to look at how many times each button was pressed instead. Then, we saw that only evenness and oddness matters in the number of presses. Knowing what each button does when pressing it once, we can figure out how a light changes when pressing any combination of buttons. In total, we're creating a transformation from button presses to light toggles. An important observation to make here is that combining 2 collections of button presses is a simple matter of addition. Before or after this transformation, it doesn't matter. From this, we immediately notice that repeating actions, that is multiplication, has that same feature. After all, we're just combining multiple instances of the same collection. Just like how we're able to bring addition and multiplication inside and outside of the modular reduction, what I've notated here as a hat on these numbers, we're able to bring addition and multiplication inside and outside of this transformation. This property is the same notion of linearity that we might have in real number land, though we don't really have a continuum to truly discuss the lines we know and love. However, we still can take a note from real numbers and use coordinate representations. This time around, instead of working with real numbers, our coordinates are these discrete modular numbers. For the basis of our coordinate system, the obvious choice is to just assign a coordinate to each button, or light, giving us a matrix that looks like this. If we want to turn off all the lights in this configuration, it's a matter of subtracting the configuration from itself. We want to find the coefficients then that transform to this negative of the configuration, which, since we're in binary land, is just the configuration itself. Written this way, we have something very similar to the types of linear systems we're familiar with, and indeed, we could try to solve it in a similar way. The common strategy here is to use Gaussian elimination, where we form an augmented matrix and then perform row operations to reduce the problem down. This begs the question, will this work for us? Or even, why does this work in the first place? When we try it for ourselves, they agree for the most part. I'm ignoring instances where the disagreement is solved by reducing the right side by modulo 2. Following through, we get the same answer on either side, again under modulo reduction. Indeed, we can play the game to see that this does actually give us a correct solution. While we do get the same answer this time, it's not always true that this happens. Backing up, the main difference is here, where there's a 3 on the real number side, but it's a 1 on the other side. If there was a non-zero value here, the last coordinate would have a fractional value. For a counterexample, let's try this one, where the last 2 coordinates are 1s. You can verify or take my word for it, that these are the answers, and they clearly disagree. That being said, we do have a correct solution to this light puzzle here. But why? To discuss this question, it'll be good to cover Gaussian elimination from the beginning. If you think about it, the choice of our basis is fairly arbitrary. Here, I'm labeling the left side with the basis our output coordinates are in, and the right side with the input basis. Sure, the standard one is intuitive, but a choice like this is just as valid. And if we were to see how our transformation works with an input in this coordinate system, we notice that it's just the identity matrix. So here we've already found the solution in this coordinate representation, so solving the problem is just a matter of making these exact button press combinations. Alternatively, we can do a little bit of simplification here, which is equivalent to just going from this special representation to our original. Just because we made a good guess for our basis, we've forgone any sort of matrix inversion or system solving here. In fact, the inversion occurs within the choice itself. This is one way we can interpret Gaussian elimination. By making successive educated guesses on the best choice of basis, we can eventually refine our choice to a guess that makes the answer easier to find. Perhaps you may have figured it out by now, but the strategy of zeroing out the lower triangular part is this guess refinement process. One caveat I would like to make, though, is that the choice of basis here, what I did for illustrative purposes, was a change on the right-hand side, the input side. We'll be looking at changing the basis on the left-hand side, the outputs, since that's actually what's related to Gaussian elimination. I should probably mention that the examples we did before were not of Gaussian elimination, but Gauss-Jordan elimination, where we cancel out the upper triangular parts as well. In terms of solving the system, the process is equivalent to Gauss-Jordan, but I want to bring attention to the Gaussian elimination part, that is, just canceling the lower triangular entries. If you were solving a system by hand, or writing an algorithm on the computer, cascading results back upward is straightforward to solve the system. When removing the subdiagonal entries, we're effectively decomposing our transformation into its matrix representation with the different output basis, and then changing the basis back into the original one. The strategy we use here is based on an algorithm called LU factorization in the world of numerical analysis when looking at the real numbers. The idea here is to write our transformation as a product of a lower triangular matrix and an upper triangular matrix. This is useful because we go from an arbitrary system to two triangular systems, where a simple technique of back substitution allows you to easily solve for the unknowns. There's a small detail about the potential for row swaps, and that forms the basis of PLU factorization, where we also pull out a permutation matrix that represents these row swaps. The neat thing is that we're always able to choose a new basis that has only one vector change, and that change will zero out the lower triangular entries in each column as we get there, without messing up any prior columns. For our case here, filling up the left column with 1s gives us such a matrix. In general, assuming the upper left corner is non-zero, we can cancel out the subdiagonal entries by multiplying by this, which is just a shear matrix. For those familiar with block matrices, we have something of this form. The inverse is just a negative of the original shear. You can verify this with the full matrix and a bit easier with block matrices, but the main focus here is the change of basis that's going on. Since only the first vector changes, this sum here, containing the other vectors, is the same in both coordinate systems. Going from u0 to v0, we're adding the sum, and from v0 to u0, we're subtracting that same sum. The reason for choosing this change of basis in particular is because if we write out what that first column looks like, it simplifies to v0, scaled up by a00. Looking at the coordinate representation, that's how we get a00 in the first row and zeros everywhere else. So here, I'll write out our matrix A with the product of this change of basis, what I'm calling L1, with its inverse. If we pull the right change of basis into the transform, we're left with this product. Alternatively, if we were just solving a system like this, we would apply the transformation to both sides rather than just using the inverse like here. The same transform being applied to both sides is why the augmented matrix technique works. Notice that the non-zero assumption at the beginning plays an important role since we're dividing for that upper left entry. If it's 0, we first perform a row swap to replace it with a non-zero entry. If every entry is 0, then we can skip that row since we already have what we want. In our case, our first step is the addition of every other state into the first vector, so that we have a fully lit board for the first coordinate. This was chosen to match the first column vector. We ignore division here since it's always by 1. Of additional note, since negation does nothing in the binary field, the change of basis matrix is its own inverse. From here, we want to find the next transform. One important observation to make is that we need to keep the first basis vector intact, since otherwise we'll be losing these zeros. Moreover, we don't have a need to write any of the following vectors with the first one. In terms of the augmented matrices, this is effectively combining lower rows into the first one, which is not at all necessary. For factorization, it kills the lower triangularity that we want the change of basis matrices to have. Because of this, it makes sense to just write the last 4 new basis vectors in terms of the last 4 old ones. Effectively, we're looking to modify this lower submatrix here so that we might as well use the same strategy of zeroing out the sub-diagonal elements. However, we have a 0 in the upper corner here, so we'll have to issue a row swap. I choose to switch the second and third rows here. The corresponding matrix looks like this, which modifies the change of basis matrix by permuting columns. This is because the input coordinates are swapped, so to get the same output, we can swap the columns in turn, so that the sum is still the same. The problem with this is that we lose lower triangularity, since the diagonal entries are all 1s. The leftmost column here being swapped introduces values in the upper triangular part as it moves towards the right, but we can go back by swapping rows. First, these two swaps, permutations, in tandem will never move a diagonal entry out of the diagonal. You could verify this for yourself. Second, we restrict our swap to the rows of the transform we haven't locked in yet. The corresponding column swaps in the change of basis matrix will only ever be between columns that have zeros in the subdiagonal entries. The net effect looks like pulling the permutation matrix through to the other side and permuting the rows of the subdiagonal entries, though we don't really see that last part for this case. Now that we have a non-zero entry here, we can zero out everything below it. Preserving this first vector, along with the last 3, we can set v1 equal to u1 plus u3 plus u4, so that our transformation matrix takes this form, with this new second basis vector v1. We can see that this introduces non-zero entries in the second column of the change of basis matrix, but they're all still below the diagonal. Now we have 3 more rows. This time, the same last 2 rows need to be cancelled out, and the process is pretty much the same. We're now left with a 0 in this 4th entry on the diagonal, so we can do a little swap like before. Pulling the permutation into the change of basis matrix, we still have the column swap, which we can resolve with a row swap, and that gets pulled into the permutation matrix like so. We now have a permutation matrix representing the row swaps between rows 2 and 3 and rows 4 and 5, followed by a lower triangular matrix and an upper triangular matrix. If we wanted to solve this system for a starting configuration, like this, we can write out the coordinate representation in the standard basis. Reversing the permutation is straightforward, since it's just 2 swaps. Notice that expanding out with the basis, we still have the same configuration. This triangular solve is pretty easy through forward substitution. Intuitively, if we wanted to find the coordinates under this basis, we have the first coordinate immediately, since that corresponds to the only basis vector with a non-zero center. Then, after seeing the effect of the first coordinate, the bottom cell doesn't need to be hit, and we can keep going and everything follows in a similar way. Inverting our transformation in this coordinate system is done through back substitution now. This gives us the set of buttons we should press to turn everything off. And indeed, that's what happens. I could end this by testing what we found on the classic 5x5 game, but since we've gone through the trouble of deriving the full matrix factorization, there's something else I want to look at. Since we're looking at such large matrices here, I'm using boxes instead of numbers, where a lighter box means a 1 and no box means a 0. Here's the process of solving one starting configuration. One significant difference from the 5-cell example we were looking at before is the existence of empty rows at the bottom of U. 2 of them, in fact. We know that PL is invertible since they're equal to a sequence of row swaps and shears. Each of these operations is invertible, so we can just cascade backwards. This is as expected since PL should just be a change of basis matrix. U is the same transformation as A, but it maps to a different coordinate system. This means that this lack of invertibility on U says something about A. Well, how U is written, we know that its range, all of the vectors that it could output, does not contain any vectors with non-zero entries in the last 2 rows. Additionally, since all of the other diagonal entries are 1, we can use back substitution to show that any vector with zeros in the last 2 rows is still in the range, just like how you solve a system from row echelon form. The last 2 rows correspond to these basis vectors. No matter how hard we try, it is impossible to solve such boards since we will never be able to toggle just these lights. Of course, this is not an exhaustive list of impossible states by any means. So if 2 basis vectors are unreachable and we have the same number of lights as buttons, then one might think that the 2 buttons are redundant. This corresponds to the null space, and the intuition is related to the rank nullity theorem, which I won't go into detail here. Pressing these last 2 buttons are respectively equivalent to pressing these button combinations. In order to find these, we can look at where U maps our last buttons to, and then use back substitution on the first 23 columns to find out what button combinations map to each. Since they have the same effect, if we combine each one, as well as these 2 together, their net effects should all be 0. And so I'll leave you here, with this animation showing that it is indeed true.